Cascade controllers have a primary and secondary controller, where the primary controller gives a set point to the secondary controller. Let me just give an example of this. Let's say you have a tank and you want to try to maintain a level in that tank. So you have a level transmitter and then a level controller, and let's say your actuator is controlling a valve, and you can send a signal directly to that valve to open or shut it. So this would be a standard PID controller. But let's say there's a disturbance upstream where the pressure fluctuates up and down, and that changes the flow into the tank. Well, one of the things that you can do is set up a cascade control system where instead of controlling directly to the valve, you would have to add something that would measure that disturbance. Like instead of a level transmitter, this is going to be a flow transmitter here. Okay, a flow meter, and then that is going to go to a flow controller, and then the flow controller will change the valve. And then the level controller, which is the primary controller, is going to send a set point to the flow controller. So even if the pressure over here changes up or down, it's going to catch it with this inner loop right here. So this is the inner or secondary loop, and this would be your primary loop, the level controller. That's the thing that you're trying to control in the end. So that's an example of a cascade control system. You have a primary and secondary. We're going to do the same thing though with the temperature control lab, and set up a primary and secondary controller and tune them and then test it. Alright, if you want to follow along, here's the link to the source code, and that will bring up some things that we want to check out, which are standard PI control right here. And then if you go down, you'll see this is going to be the one that we're going to do with the cascade control. So we're going to tune it in simulation first, and then as a very last thing, we're going to try it out with the we're going to go ahead and test it on the device. Okay, so there's code for each of those, the simulators as well as the actual running on the TCLab. Let me go back here first, and let's just talk a little bit about what we're going to be doing with this cascade control system. So we have our TCLab device, and this is temperature 1 and there's temperature 2. Okay, so temperature 1 is right here, and then temperature 2. Here's our heater 1. Now we're not going to be using the heater 2 for this one, just the heater 1, and we're going to try to control temperature 2 with heater 1. So standard PID controller is we could do a step in our Q1 and then measure the response in temperature in T2, and then from that design a PID controller that would automatically adjust Q1 to try to change T2 to a certain set point. But the other thing that we can do is measure our T1 and then set up an inner loop on that, where we have a set point for T1, and then the primary loop for T2 is going to send a set point for T1. Alright, so the very first thing that we want to do is just set up a block diagram. Just make sure we know what signals are going where and what we're trying to control. So the very first thing is to design, and let's just draw the block diagram for this. So the standard control system would be to have this is going to be a temperature 1 set point or temperature 2 set point. Let's just start with temperature 2 set point, and then we're going to compare that set point with the temperature 2 measured. Alright, and then we're going to have our controller. This might be something like a PID controller, and the PID controller is going to then go through our TCLab system, and this is our Q1 value, and then it's going to give us a different T2 value. If we have any measurement dynamics in here, we can put in a block for the measurement. This is going to be the T2 sensor, and we're going to measure that, and this is our standard feedback control loop without any cascade control. Now let's say we wanted to change this a little bit, where now we're going to have a T1 set point instead, and we're going to measure T1, and we'll have our T1 measurement. Okay, and I'll change this to T1 as well. So here's our inner loop now. And then we have how T1 affects T2. So this is also our TCLab system. It's just the heat transfer from T1 to T2. And then we're going to measure that one as well. So they'll have another measurement here. This is going to be our T2 measurement. And that's going to come back over here, and I'm going to come back into a comparison. Now we're going to have a T2 set point, which is then going to go into another controller. It's going to be another PID controller, and that's going to send out a T1 set point. So inside here, this is our inner loop, and then our outer loop is right here, our primary and secondary loops. Alright, so we see the flow of the signals and how this cascade system is going to work. Let's go ahead and test this out with the simulators now. So now we want to tune these. We have the first one, which is the basic PID controller. We'll just see how good we can get, if we even need a cascade control system. And then we'll go on to the second one, where we actually tune the cascade. Alright, so let's go ahead and start with the standard PI controller. The thing that you want to do here is come down to the bottom right, select the get code, and that'll give it to you in raw format. Start up your Jupyter notebook, and once that starts, then what you want to do is just come to some place where you can find it again, click new, and then a Python 3 notebook, and then go ahead and just paste it in and run it. Control Enter runs that, and it will come up with the sliders. The thing that we want to pay attention to on this is the integral absolute error. Right now it's 5,500. Let's go ahead and just increase the gain and see what that does. We have temperature 1, but we're really not using temperature 1 at all. We're only using temperature 2 and how close it's getting to the set point, and then we change heater 1 here on the right. Alright, so as I increase the KC value or decrease the tau I value, you can see that it's changing the IAE value, the integral absolute error. And if I just change that a little bit higher, I'm going to go all the way to 10. And if I go all the way down, you're going to see a lot of oscillation. So this is kind of an unstable system because there's so much delay there. So I've got to back off on the tau I value. Alright, and so you can change this and try to get it down as low as you can. You can see that I went just a little bit too far there. And here is about as good as I've been able to get it, about 2400, but you can play around with different values, try to improve that. We're not actually going to use this one or test it, but I just wanted to show this one in comparison to the Cascade Control system. Alright, let's insert a cell below, and then here we'll do the Cascade Control system. Alright, if I come back here, I'm going to come down to the second one, which is the Cascade Control, and we're going to tune this one in simulation before we actually implement it on the TCLab. So come down here to the Get Code again, select all the text, and then go ahead and paste it back into your Jupyter notebook, and then you can run it again. Alright, so this one has two PID controllers. Here's your inner loop on the KC1 and tau I1, and then the outer loop there with KC2 and tau I2. Okay, so the very first thing that we want to do in a cascade control system is we want to tune the inner loop first. And what that would typically mean is that we put the primary controller, the outer loop, in manual and do step tests with the inner loop to get a good model. We close the inner loop, and then but we're not going to do that here. We have a simulator, so we can increase this, try to get the PV to match up with the set point. Alright, so it's better tuned, it's following the set point, and then we can start tuning the outer loop. We want to watch the integral absolute error here. Alright, and so I'm going to continue to increase this one a little bit more. We go to 7.5 and then 80. Alright, so we're down to 2383, 2384. Alright, you might be able to improve it just a little bit more. There's 2340. Okay, I'm getting down to 2290. And it looks like 2290 is about as good as I'm going to get. Alright, so just in comparison, this is 2290. That's the integral absolute error between the set point and the PV. And then up above, just with regular PI control, the best I could get is about 2465. Alright, so let's implement these now in our controller. These were the values. I'll go ahead and just take a screenshot of this just to be able to compare it for later, and just to see how well it performs in relation to our actual PID Cascade controller that we're going to implement. Alright, I'll move this off to the side. Let's go get our final piece of code that we're going to be working with here. Alright, and it's down in the web page. I better go back here. Okay, so it is right here in the test Cascade Control with TCLab. This one's a little bit longer script, but it will run the PID controller and generate an animated plot for you as well. I'll go ahead and click the Get Code, select it, and we can run this inside the Jupyter notebook as well. Alright, so I'll go ahead and insert one more below it. Alright, and then run this one. And it's going to connect to the TCLab and then generate an animated plot here inside the Python notebook. You can see it hasn't changed set points yet, but then when it does, you're going to see this T1 and T2. The set point for T1 is going to change because it's receiving a new set point from T2 controller. Alright, and we're going to watch the integral absolute error as that grows. Actually, what I need to do here is restart my kernel because I forgot to put in the new tuning values there. So let's go ahead and do that first. Just put in the new tuning values because the ones in this script are default, and we want to be able to change those to the ones that were in our simulation so that it is close as possible to what we simulated. Alright, so we just need to change this first part right up here. I'll go ahead and bring those up again just so we can see them. Okay, 7.5 and 80. Alright, I'll just go ahead and put those in here. 7. Alright, 7.5. And then change that to 80. Alright, and then we have two more, 6.5 and 90. Alright, 6.5 and 90, and that was pretty close to what it was before. And alright, and it looks like my temperature control lab is a little bit warm right now, so I need to wait for it to cool down, or I can swap it out with another one that I have here. So I'm just going to do that really quick, is just swap out my TCLab with another one. Because if they're warm, then it gives you a much better performance because it's already heated up. It doesn't need to take that time. So let me go ahead and just plug this in, and I've restarted my kernel, and then I'll restart the controller. Again, I just put in the new values right here, and then we're going to test it again. And there's some code in here that it'll wait for it to get below 25 degrees Celsius. If it's not, then it'll make you wait for that. Alright, and looks like I probably want to scale this a little bit better to 100% or 100 degrees Celsius because it looks like this is going to go off the scale, okay, on that set point. So I'll do that in the source code on the web page, and then you can use it later. Hopefully it'll be scaled correctly for you. Okay, so we're just going to watch this, and I'm going to just bring up this other one off to the side, and we'll see how well it agrees with these measured values that we get from the Cascade Control. So I'll go ahead and pause it right now, and then we will start it in a little while. It's going to take about 15 minutes to complete this test. Okay, you can see that it's almost to the set point. It might overshoot just a little bit, but it looks like it's following fairly closely to what it predicted. It looked like it said that we was going to get to the set point at around 400 seconds. It got there a little bit faster. You can see the integral absolute error right now is around 2,400, whereas the predicted one was about 2290. Okay, so fairly close. You can see the set point coming down now. It's going too high on temperature 2, so it's sending a set point to temperature 1 to lower itself. And you can see it's following that. It's trying to follow that with the inner loop that's tuned. It looks like temperature 2 is now leveling off, and it's adding more heat, Q1, to try to meet that set point that's now rising just a little bit right here at the end. You can see that set point for T1 is rising, temperature 2 is right there at the set point. Okay, so I could let this go for about another 15 minutes, but it's going to level out kind of like the simulation shows, and you're going to be able to see just a little bit of oscillation there, but overall it's just about there. The integral absolute error isn't going to accumulate a lot more just because it's already near the set point and will likely stay pretty close. So expect it'll go up to about 2,500, maybe 2,600 in the end. Okay, so this is the Cascade Control. We've implemented a Cascade Controller and both simulated it, but then also did a physical test too with the Temperature Control Lab. I'm going to come back here and just review some of the other solutions here. Here was the standard PID controller, and you can see the block diagram and the measurements. And then if we do a Cascade control system, then we have this inner loop and outer loop as well. And there you can see my tuned system There's just some other values, maybe just a little bit better, and then here are the values that I came up with before. And then you could finally see the full 15 minutes here with about 25:38 for the integral absolute error.